Hello class, this is a video tutorial on dilations of functions. A dilation can be thought as of stretching of a function. So dilations can be summarized into two types: vertical dilations and horizontal dilations. So a vertical dilation is the stretching of a function so that the distance from f of x to the x-axis is increased by a factor of a. So take a look. Take a look at the original function of f of x. Just to emphasize this point, we'll look at the distance between the x-axis and the vertex. Notice that it's been stretched by a factor of 3. Okay, so the distance was first 1, but now it's become 3. And this is accomplished by replacing y with y over a. So let's show this using the function. So we have the function f of x equals x squared minus 2x. If we want to vertically dilate it by a factor of 3, we replace y with y over 3, and we evaluate it until it becomes y equals. So multiplying both sides by 3, we get 3 f of x. 3 times the function is equal to 3x squared minus 6x. So in reality, this function g is actually 3x squared minus 6x. For horizontal dilations, it's the stretching of a function so that the distance from f of x to the y-axis is increased by a factor of b. Factor of b. This is accomplished by substituting x with x over b. So just to emphasize this again, take a look. The original function, that one there, the distance from the vertex to the y-axis is a distance of 1. If we stretch it by a factor of 3, the new distance from the x-axis is 3, because 1 times 3, well, it's 3. Notice though that the distance from the x-axis remains the same. It's only from the y-axis. So let's show this algebraically. We have the function x squared minus 2x. If we replace f of x with x on 3 and substitute it into the function, so here's my function, x squared, and we're replacing it with x on 3, as well as 2x with x on 3, we get the function 1/9 x squared minus 2/3 x. So this black function g, call it g of x, is actually equal to 1/9 x squared minus 2/3 x. Enlargements or compressions are a combination of vertical and horizontal dilations. Enlarged shapes are similar figures to the original, so maintain the same angles and have the same factor dilation on the x and y axis. So take a look. If we substitute y with y on a, for this to be an enlargement, we also replace x with x on a. And here's a example of what this might look like. So we have the original triangle ABC, and it's been enlarged to become a prime, b prime, and c prime. Notice also that 1 times 1.5, 2 times 1.5 is 3, and 3 times 1.5 is 4.5. Okay, so let's apply the dilations listed and sketch the resulting functions. So here's our original function, and we want to dilate it vertically by 3. Okay, so here's my original function. Let me copy this. And for vertical functions, just so we remember, vertical dilations, we replace y with y on a. Okay, so here we have y equals, if we take this y on 3 is equal to x squared minus 4x plus 3. We resolve this, y equals 3x squared minus 12x plus 9. And now this would look like the following. Copy this. So, because we're enlarging it by a factor of 3, because this is at negative 1, it will now be at negative 3, so all the way down here. But everything else will remain the same. So, look somewhat like this. That is a rough sketch of what that might look like. Alright, let's do this again. Let's take the original function. And we want to dilate it by a factor of half. So y equals, so this becomes y over half equals this function. And now we're multiplying both sides by half, giving us y equals half x squared minus 2x plus 3 over 2. And what this might look like, here we go, whoops, here we go. Well, no need to look at this one, we just need to know the appearance of this. Well, if this is a distance of 1, to be vertically dilated by half means it will be half the distance from the x-axis. So it will now be here. Using just this point, we can see that this parabola will look somewhat like this. It's been flattened out just a little bit. And there we go. Let's do this again with horizontal dilations. Now with horizontal dilations, just so that we can recall, we replace x by x over the factor that we want. So here's our original. And we're replacing this with x over 2. So f of x over 2, this will give us x on 2 squared minus 4 x on 2 plus 3. Expanding this, we get x squared with a quarter minus 2x, because 4 and 2 will cancel, giving us 2 plus 3. So now what this would look like is the following. Copy, copy, paste. It's one slightly harder now. Without even having to look at this graph, we just look at the distances between each critical point and the y-axis. So, if this was a distance of 1, to be given a dilation of 2 means this distance will now have doubled, meaning if this were 1, it will now be at 2. If this were 3, it should now be at 6. So 3, 4, 5, 6, all the way at the end there. And this position of 2 times 2 would be at 4. So be at that point there. So this is a horizontal dilation. It will look somewhat like so. Oops. There we go. Moving right along. Let's do a horizontal dilation of 1/4. Of 1/4. So we're replacing this with x over 1/4. So f of x over 1/4. If you think about this, this is the same as replacing this as f of 4x, because x divided by 1/4 is the same as multiplying by 4, which is now going to be 4x squared minus 4x plus 3, giving us 16x squared minus 16x plus 3. Taking our original function in the graph, let's take a look at what this might look like. Let's try and fit it in over here. There we go. So now if it's 1/4 the distance, so if this is a distance of 1, it will now be 1/4 in. So it should be here. If this is a distance of 3, it should now be 3/4 in. So it should be all the way, that's half, 3/4 is here. If this was a distance of 2 from the y-axis, it should now be 1/4 that length. So 1/4 of 2 is half. So we now have this teeny, really squished parabola that looks somewhat like this. So I hope that gave you an insight into vertical and horizontal dilations and the few examples here in this video. Hope to see you in the next video. Best of luck.